Hello and welcome to another video of Smarty Academia International. Our today's topic is going to be on numbers, approximations, errors, and scientific notation. Let's look at the type of numbers that we have. Numbers can be classified into two major categories, one being real numbers and the other being complex numbers. Real numbers can be represented by a symbol that relates to R, and complex numbers can be represented by C. We've always understood that root of any negative number is not possible. To overcome this is the type of numbers we classify as complex numbers, and it has major utility in many engineering aspects. To understand this, we basically equate -1 root as something we call iota, that's IOTA. So basically, in engineering or in mathematics, numbers can be classified into two major categories, real and complex, and we say that any number has two parts, real parts and complex parts. The details of the complex numbers and the combination of real and complex numbers we will study in our complex number section. But for now, to understand that -1 root is basically equals to iota. So in simple words, if I say -3 root, this can be written as 3 times root of -1, or in simple terms, -3 iota. So that's all for now for the complex numbers. Our main topic today is basically understanding the real numbers. Real numbers can be further classified into two major categories. One is the rational number, and one is the irrational number. Rational numbers are represented by Q, which means the numbers that can be written in the form of fractions, which means P over Q. Whereas irrational numbers are represented by Q naught. That means the numbers that cannot be represented in the form of rational numbers or fractions. Now, in this case, we need to know that Q should not be equals to 0, because we know that no number can be divided by 0. That's impossible. Now, to understand or categorize what are rational or irrational numbers, I can simply say that if I say I have a real line, this is, let's say, my real line, and it extends until from -infinity to +infinity. The center is 0. We have 1, 2, and continuing like that. On the left side, we have -1, -2, and continuing like that. We know any number which is on the right side, it's increasing. That's just how the numbers are increasing. And if I go to the left side, we know that the numbers are decreasing. In this particular real line, we have infinite numbers. In fact, if I say real numbers between 0 and 1 are also infinite, because we have many combinations of numbers that can go until infinite. For example, 0.1, 0.11, 0.111, and so on and so forth. So this is the beauty of numbers, that we have infinite numbers. In fact, the range of numbers between 0 and 1 is also infinite. But we need to categorize that what are our rational numbers and what are our irrational numbers, because this is a very important concept. Remember, any number are rational numbers. Okay, for instance, 3 is also a rational number because I can write it as 3 over 1. Similarly, 4 over 5, this is already in fraction, can be written as rational number. Similarly, decimals can also be written as rational numbers. For instance, you have 0.1 can be written as 1 over 10. Similarly, 0.2 can be written as 2 over 10. Similarly, 0.5 can be written as 1 over 2, and so on and so forth. Even the recurring decimals, let's say 0.999999, continuing, can be written in the form of 4 over 9. You can check from the calculator that this is the right thing, can be written in this form. Now the question comes, what are irrational numbers? So irrational numbers are, in simple words, non-recurring, non-terminating decimals. The type of decimals that have no pattern and they do not stop. Here we know that the decimals are recurring, and it keeps on going. It's not terminating, which means it will never end, but still it has a certain pattern. And if it has a certain pattern, we can always write it in a form of fraction. So we know that pi is a very famous number, which is equals to 3.14 blah 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 blah. Similarly, e is another irrational number, which is 2.71, and keeps on going without any recurring aspect to it. Similarly, root of the prime numbers are all irrational numbers, because you would see that they are non-recurring and non-terminating. For instance, root of 2, the root of 3, the root of 5, and so on and so forth. So these are all irrational numbers. Now, although this is not what we need to know, but obviously this is a really important concept, that how do I know that I can write my non-terminating recurring decimals in the form of fractions? Let's try to see some examples. For example, we have recurring and a non-terminating decimal, 0.3333, and so on and so forth. Let's assume that this is equals to x, and I can write 0.3333 and so on as x. Now, if I multiply both sides by 10, let's say 10 times this, and obviously 10 times this, I know that multiplying by 10 will move my decimal 1 unit to the right. So 10x is going to be equals to 3.3333, and so on and so forth. Similarly, I knew that my x was equals to 0.3333, and so on and so forth. And if I wish to subtract this, so what will happen is that this 3 and this whole thing will cancel out, obviously, and I will be left with 9x equals to 3. And simply taking this down, my x becomes equals to 3 over 9, and simplifying it, it will give me 1 over 3. So basically 0.3333 so on, I can write it as 1 over 3. And there's another way to write this. It's 0.3 bar, whereas the 3 bar, whereas this bar represents what digit is being repeated constantly. So this is a way to write our recurring and non-terminating decimals. Let's try to have another example. Let's say instead of 0.33, we have now 2.136, 136, 136, and so on and so forth. What does this mean is that my repeating section is 1.136. So I can put a bar here, which means my 0.136, 136, 136. This is the repeating or the recurring aspect of my decimal. How would I write this in the form of a fraction, or is it a rational number? Let's try to check that. Similarly, I can suppose this is my x, 2.136, 136, and so on and so forth. Now, instead of multiplying by 10, I will multiply this both sides by 100, and you would see why. When I multiply by 100, I know my decimal will move 2 units to the right. So my 100x will basically turn out to be 136, 136, and so on and so forth, right? The only thing is that my decimal moved 2 digits to the right. Similarly, I know my x was equals to 2.136, 136, 136. I'm trying to write it as like making sure my decimal falls below the decimal. Now, if I subtract this, and you notice, these things simply cancel out. The only thing left is this. So this becomes 9x. So if you just use the calculator, 230.6 minus 2.1 is basically 211.5. Now still, we know this is terminating, so we have converted our non-terminating to terminating decimal. Now, using my simple conversion of decimal to fractions, I can just write that 2115 over 10, because I know dividing this by 10 will actually make it 2115. So this is 9x. Now simply, I can take this 9 to this side, so my x will be equals to 211, or in simple words, I can just simply write 1 here and cross multiply. So 9 times 10 is 90x equals to 2115, and my x will be equals to 2115 over 90. And I can just simplify this. So it become 22, so it become 47. So 47 over 22 is basically 2.136, 136, 136, and so on and so forth. So that means this is indeed a rational number. Now let's try to look further into these real numbers. So real numbers can be classified into 2 major categories. One is the integers, and one is the decimals, if I may. In decimals, we have talked about 2 types again. One is terminating, and one is non-terminating. Just looking into a different aspect of how you can classify real numbers. Terminating, as I said, would be 0.4, 0.5, 0.136, or 2.14, 5.65. The numbers which are simply terminating means the decimal terminate. Non-terminating can be further classified into 2 major categories. One is recurring, and one is non-recurring. And we have said that all of these numbers, these are all rational numbers, which is Q, while these ones, the categories in this thing, are irrational numbers. And we have discussed it, like 0.333, also a rational number, 2.136, 136, also a rational number, whereas pi, e, root 2, root 3, these are all irrational numbers. Similarly, integers can be classified into many categories. We have prime numbers, we have natural numbers, we have whole numbers, we have even numbers, we have odd numbers, we have square numbers. Like, we can classify them into multiple categories. Integers, we know, can be positive, negative, or 0. Whereas we know prime numbers are those numbers which are only divisible by themselves, starting from 2. So 2, 3, 5, 7, 11, and so on and so forth. Natural numbers are the numbers that start from 1 and just continue. Next, integers. Whole numbers is just adding a 0 to natural numbers. These are all the numbers. Even numbers are the numbers which are divisible by 2. So we have 2, 4, 8, 10, so on and so forth. Odd numbers are the numbers which are not divisible by 2, 1, 3, 5, 7, and so on. Square numbers are simply squared numbers, like 1 squared, 2 squared, 3 squared, and so on and so forth, which correspond to 1, 4, 9, and so on. So these are all the type of numbers that are, and again, these are all rational numbers. So this is how we can see the structure of real numbers, and we can know that how all these numbers can be classified as. Now let's look at our next topic, which is approximations. Approximation is basically to approximate our particular numbers or our measurements, and this is what we need to understand. To start up with, we need to know the place value, although it's a very basic concept that we learned in our early years, but I think it's important to make sure that we do understand this concept. So let's say we have a number 4186.316. Now we know this is the decimal. The very first number on the left side is what we call the ones place value. The second one, what we call the tens place value. The third, what we call the hundreds place value, and this is obviously thousands. Then we have 10,000, 100,000, and so on and so forth, after 1,000 million, obviously. But what happens after the decimal? We call this tenths. This is a very important thing you need to understand. This is what we call hundredths, and this is what we call thousands, and similarly 10,000s, and so on and so forth. So this is the place value of numbers including decimals. So when someone tells you to round your number to the nearest tenth, it means this is the digit where you want to round it to. The rule of rounding is like pretty important. Let's say if I say round this number to the nearest thousands, it means we need to round the number to the nearest thousand. So if we draw the line, we know that the lower thousand range is 4,000 and the upper thousand range is 5,000. So this number lies somewhere here, which is 4186.316. So it is clear that this is near to this 4,000, right? But what is the rule in this case is that whatever digit you want to round it to, you just look at the next digit. And if it is 5 or greater, you add 1 to the previous digit. If it is less than 5, then you keep this digit. So in this case, we know 1 is less than 5, so we'll only round it to 4,000. Let's try another example. Let's say I say round this number to the nearest hundredths. Hundredths means this is where I want to round it to. So what this means is I can just simply say 4186.316, right? So this is where I want to round it to. So the next number I know is greater than 5, so I just have to add 1 with this. So this will be 4186.320. So this is what I've rounded my number to. So this is really important in approximations. We need to understand that how we are rounding. This is the rule of rounding stuff. Usually when it comes to approximations, there are two basic terminologies that are very important. One is the decimal place, and the second is the significant figures. Decimal places are the numbers which come after decimals. For instance, if we have 0.00784, so we know there are 1, 2, 3, 4, 5 decimal places, what we call DP. Whereas the same number, what we call significant figures, if I write here 0.00784, you start the significant figures or the significant numbers which start from a non-zero digit. So these are all zeros. We do not consider zeros on the left side. The first significant digit would be the number which will be non-zero. So that's the first significant digit. This comes the second significant digit. This comes the third significant digit. So we have 3 significant figures in this particular number. Similarly, let's say we say that we have 3400. In this case, we know there are no decimal places because there's not a decimal number. So there's no decimal place in this case unless we write 0.0 here. But let's say 3400. In this case, the significant figure or significant digits would be 4. You will consider these zeros because they're after the non-zero digits. So it's basically 4 significant figures. So this is a really important concept that you need to understand, rounding your numbers to whatever significant figures or whatever decimal places. And as we move forward with the questions, these terminologies will be more relevant. Now, in terms of in the questions, you will always round your answer to 3 significant figures until specified otherwise. If the question does not say to what number you need to round your answer to, you would try to round it to 3 significant figures. If the question specifically says round your answer to 4 decimal place or 5 decimal place, then you will follow the question instructions. Now, in order to understand further, now we have understood the concept of approximations. So this clearly says that whenever we are measuring anything, we always approximate. No matter how precise we are with our calculations, yes, we can minimize our error, but we cannot eliminate it. There is always some kind of error available or some kind of error always present in the measurements. That is reason why we need to understand what is the limit of our errors or what is the range of values that can define our measurement. In this case, we really need to understand that our error in measurement is always equals to plus minus half of the smallest division of our equipment. Consider we are measuring the length of this pencil using the centimeter scale. So as visible, the length is basically 9.0 centimeters. There is a reason why I did not write 9 centimeters and I wrote 9.0 centimeters. This is because if you see, there is the least division in this is 0.1 centimeters. So this least division defines that what decimal place I'm going to use. And this is like really important. If an equipment is not given, so you understand the least division by seeing the number of decimal places. For instance, if it was written 9.00 centimeters, then you know that the least division is 0.01 rather than 0.1 in this case. Therefore, coming back to the question, finding the length and the range of accuracy for this particular measurement. So we need to find the least division. which can be seen both from the equipment as well as the decimal place used. So in this case, it's going to be 0.1 centimeters. So what is the range of values? The range of values, as discussed, we need to add the error with it, which is plus minus half of the least division. So we'll have 9.0 plus minus half of the least division, which is 0.1. And this is your centimeters, means range of values. If we do half of 0.1, it becomes 0.05. So we have two ranges basically. One is the lower bound and one is the upper bound. The lower bound is 9.0 minus 0.05, and the upper bound is 9.0 plus 0.05 centimeters, that is. And by subtracting this, I get 8.95 centimeters. And by adding 0.05, I get 9.05 centimeters. So my range of values, obviously, using my equipment, I measured the length of the pencil as 9.0 centimeters. But the range of accuracy, the lower bound is 8.95 centimeters, and the upper bound is 9.05 centimeters. So that is your lower bound, what we call, and that is your upper bound of your measurement. And the error, if you see, is basically 0.05, which is the same thing, half of the least, or the least count of the smallest division, which is 0.1, which is 0.05 centimeters. Now, in this case, by understanding the term, now, if you notice that the range of the values will always be equal to the least count, which is 0.1 centimeters in this case, whereas the error would be either in the positive direction, 0.05 centimeters, or in the negative direction, 0.05 centimeters. So I can write that in terms of accuracy, the length of this pencil is basically between 8.95 centimeters to 9.05 centimeters. This is what I call the range of accuracy. Now consider a rectangle with dimensions 78 centimeters and 24 centimeters. Please note that it has been given 78 centimeters. So it's not given 78.0 centimeters. So in this case, the least division would be 1. So it's written 78 centimeters by 24 centimeters, the dimensions. So the least count in this case will be the unit place value, which means the smallest division, or in simple words that I'm going to use for my ranges, is going to be 1 centimeters. All right, so let's try to find the upper and lower bound for this. Basically, the task here is that I want to find the accuracy for perimeter, and I want to find the accuracy for the area, like the range of accuracy for area and perimeter. Once I've measured, remember, area and parameters are calculated, they're not measured. The measurement is only the dimensions, length and the width. So we want to see that because we will have some error in our measurements, how that error will propagate towards our calculations of perimeter and area. So let's see that. So first of all, let's try to find the upper and lower bounds for the area. So as discussed, the error is going to be, for example, we have 78 centimeters. This I can write as 78 plus minus half of the least count of the smallest division, which is 1, which in this case is 0.5 centimeters. So that means my upper bound, I'm just going to use UB for my upper bound, is going to be 78 plus 0.5 centimeters, which turns out to be 78.5 centimeters. Similarly, my lower bound would be 78 minus 0.5 centimeters, which turns out to be 77.5 centimeters. Similarly, for the width, I can calculate like 24 centimeters can be written as 24 plus minus half of 1, the same way I did for 78. The upper bound for 24 is going to be 24 plus 0.5 centimeters, which would be 24.5 centimeters. And the lower bound for 0.4 is going to be 24 minus 0.5 centimeters, which will be 23.5 centimeters. Now I need to basically find the parameter. So my parameter again would be something lower bound, upper bound, and my parameter in between. Remember, as we saw here, the error will be basically same on either sides. All right. So let's try to see the lower bound. We know that the parameter is basically sum of all sides. So how do you get the least sum? Is basically by adding the least numbers. So the lower bound of the parameter, that is, will be adding the lower bound of all the sides. Got it? So that would be 77.5, which is in this case, so you see these are the lower bounds. Okay, plus 77.5 plus 23.5 plus 23.5, simply adding the lower bounds. And we know the parameter sum of all sides, so here would be like 78 centimeters, 24 centimeters. So the lower bounds, if I want to write the lower bound values here, would be basically 77.5 centimeters, 77.5 centimeters, 23.5 centimeters, and 23.5 centimeters. So just adding all these lower bound values will give me the lower bound value for my parameter. So adding all of this, you would see that we get 202 centimeters. Similarly, finding the upper bound of all the parameters is adding all the upper bound values. Similarly, 78.5 centimeters plus 78.5 centimeters plus 24.5 centimeters plus 24.5 centimeters. And if I add all these upper bounds for the parameter, I get 206 centimeters. So I know that my lower bound is 202 centimeters, my upper bound is 206 centimeters. What will be the middle thing? Remember, whenever you find the lower bound and the upper bound, in order to find the parameter, you can simply add lower bound and upper bound and divide them by 2, because you're trying to find the average value. That is what the calculated value is. So in this case, it's going to be 202 plus 206 divided by 2. So the answer here in this case is going to be 204 centimeters. So it's 204 centimeters. Now, if you notice, the error has basically increased. So this is plus 2 and minus 2. So if I want to write parameter, I can write it's 204 plus minus 2 centimeters. So before, in our calculations, my error was like for example, my measurement was 78 plus minus 0.5 centimeters, and this was 24 plus minus 0.5 centimeters. You see, the error when calculated in parameters has increased to 2. So calculations basically enhance the error. So this is something that you need to understand. It does not remain the same. So this is your parameter, and this is how the error has been propagated. Now let's try to find the area of the same. We know that area is simple length time width, and I'm just going to write the upper bound and the lower bound again. So it was 78 centimeter, and the lower bound was 77.5 centimeters. Upper bound was 78.5 centimeters. Similarly, we have 24 centimeters. So our lower bound was 23.5 centimeters, and upper bound was 24.5 centimeters for the same rectangle that I was using. So it was 78 centimeters and 24 centimeters. Now, in order to find the area, so remember the area, what will be the lower bound of the area? We know it's length times width, right? But to get the least value of the area, I know that for example, I have to multiply lower bound by lower bound, because this will give me the least multiplication. So this would be basically, in simple words, would be 78.5. Here I'm doing the upper bound, so I'll calculate the upper bound first. So I'm just multiplying the upper bound areas to get the maximum result. So it'll be 78.5 times 24.5, and if you see, my answer gets 1923.25 centimeter squared, because it's the area. So that's the upper bound for the area. Similarly, to find the lower bound for the area, I need to multiply the lower bound values, because least multiplied by least will give you least value. Maximum multiplied by maximum will give you maximum value. So this would be 77.5 times 23.5. The answer would be 1821.25 centimeters squared. So these are the lower bound and the upper bound values, if you see. So it's 1821.25 centimeters squared, and the upper bound is 1923.25 centimeters squared. So my area would be, as done in the previous case, will be similarly lower bound plus upper bound divided by 2. So this will be 1821.25 plus 1923.25 divided by 2. And if you see, my area turns out to be 1872.25 centimeters squared. So it's basically 1872.25 centimeters squared. Now, if I see the difference between these two, you will notice negative 51, and this is positive 51. And you can see how the area has basically increased. So I can write that 1872.25 plus minus 51 centimeters squared. So this is your area, and the area and the error has increased much more while calculating the area. So you need to be very much aware that these are the rules how you are going to calculate the area. In some cases, you have to think out of the box as well. Let's say I measure x as 25 centimeters, and I'll measure y as 12 centimeters. So using the same logic, I know that x is 25 plus minus 0.5 centimeters. And similarly, y is 12 plus minus 0.5 centimeters. Let's say I have a quantity z, which is basically x minus y. And I need to find the lower bound and the upper bound for this particular quantity. So if I see x, I know my x upper bound is basically 25.5 centimeters. Just remember, how did the 0.5 come in? Because there's no decimal place, so the least division or the smallest division is basically 1 centimeters, and we know the error is basically half of the smallest division, so that's half times 1, which is 0.5 centimeters. So again, and my lower bound in this case would be 24.5 centimeters. Similarly for y, my upper bound is 12.5 centimeters, and my lower bound is 11.5 centimeters. So simply adding and subtracting 0.5 with 25 centimeters and 12 centimeters respectively. Now, in order to find the lower bound for z and the upper bound for z, and this is obviously your z, about it, if you have the highest value minus the lowest value, you get the maximum result, if you understand my point, right? And similarly, if you get the lowest value of the bigger number, subtracting by the highest value of the smaller number, you will get the minimum results. Okay, example, if I subtract upper bound of x minus the upper bound of y, which is basically 25.5 minus 12.5, I get 13 centimeters. But if I subtract upper bound of x minus the lower bound of y, which is 25.5 minus 11.5, I get 14 centimeters. Similarly, if I subtract lower bound of x with the upper bound of y, which is basically 24.5 minus 12.5 gives me 12 centimeters. Similarly, if I subtract lower bound of x with the lower bound of y, I get 24.5 minus 11.5 centimeters, I get 13 centimeters. So if you see basically in this case these two are same, but usually if you see this is like really important, and that this is the maximum value and this is the minimum value, which means this is going to be my upper bound and this is going to be my lower bound of z. So how do you get the subtraction thing? If you just simply use the logic that the lower bound is going to be subtracting 25.5, which means the upper bound of x, with the lower bound of y. How you can understand this? To maximize the difference, this should be maximum and this should be minimum. This is how you maximize the difference. So this is 14 centimeters. Similarly, to minimize the difference, if I want to minimize the difference, this should be minimum and this should be maximum, given that x is greater than y, obviously. So similarly, the lower bound is 12 centimeters. The upper bound was 14 centimeters and the lower bound is 12 centimeters. And if I want to take the average of both, it's going to be simply 12 plus 14 over 2. So 12 plus 14 divided by 2 is basically 13 centimeters. So I can write z equals to 13 plus minus 1 centimeters. This is your z lower bound and upper bound, or the range of accurate values as calculated. Our next topic is the concept of absolute and percentage error. Now, there are two types of errors we can see, and obviously one is the absolute and one is the percentage. As discussed, we know that our measurements will give some sort of error. It can be minimized using more precise equipment, but the absolute error in the measurement is calculated as VA. VA is the approximated value that we have calculated minus VE, which is the exact value or the actual value, which is for a certain measurement. So this is the error. Sometimes we know it can be positive or negative. For example, the length of let's say a particular length of a particular for example, length of a particular bar is 9.2 centimeters. This is the actual length. Sorry, E for exact. Don't confuse A for actual. A is the approximated. And let's say one person can measure the length as, let's say that's one first person measured 9.3 centimeters and the other person measured as 9.1 centimeters. And if you can see, both have an error of 0.1 centimeter, but one is positive and one is negative. So in order to cover that particular sign convention, we use mod here, which means whether the error is positive or negative, we'll always get the absolute value. That's why we call this absolute error. It will always be positive. So in this case, for the first person, we have 9.3 minus 9.2 bar. The answer is 0.1 centimeter. This is the error. For the second person, we have 9.1 minus 9.2, although it will give me negative 0.1, but the absolute value is still the same, 0.1 centimeter. So both have the same level of accuracy, means both have an error of 0.1 centimeters. Similarly, I can convert this thing to percentage error by simply dividing the approximate error by the absolute error by exact value multiplied by 100 to see that what is the percentage of error for that particular measurement. The next topic is about scientific notation. Scientific notation is a way of writing numbers in standard form, which is very much conventional in physics, chemistry, biology, because this gives us a standard form of numbers that we can interpret and compare if one thing is bigger or smaller. The format of scientific notation is a times 10 power k. A is a real number with a value ranging between 10 and 1, which means it will include 1 and further, and it will be less than 10, which means that it will always be in the form of, let's say, 9.1 whatever decimal. So you always have a non-zero number here between 1 to 10 and 10 not included, obviously. And k is always going to be a positive or a negative integer depending upon what value we are going to use. Let's see, for instance, we have, let's say, 0.00003648. This is a number, and we want to convert it into a scientific notation. Currently, the decimal is here. So we want to know that, because I said that it has to be between 0 and 10, 1 and 10, and the first digit should be a non-zero digit. So that means our decimal has to jump somewhere here. Now see how many jumps it has to do. That's 1, 2, 3, 4, 5, and 6. So I can write that as 3.648. I just used the same digits after, and the number of times my decimal has jumped is what the k is all about. In this case, it's going to be -6. Now remember, what is k? If the decimal jumps to the right, k is always negative, and the value of k determines the number of times that my decimal has jumped to the right. So in this case, 6 times, so the value will be 3.648 times 10 power -6. Now, if the question says round this to two significant figures, you can say 3.6 times 10 to the power -6, two significant figures. If the question says round the answer to two decimal places, you can say 3.65, because 8 is greater than 5, so the 4 needs to be added by 1. So times 10 to the power -6, this is two decimal places. So the approximation can vary, like where you want to approximate, to what significant figure or what decimal place. Let's see another example. Let's say we have 8564.239. Now in this case, it's clear that the decimal has to move backwards here, because we know that I need to write one non-zero digit and then the decimal. So it has to go 1, 2, and 3 units to the left, which means I can write this as 8.564239 times 10 power positive 3. And as I said, in this case, k would be positive when it goes to the left side. So it's like kind of a negative convention. Right is negative and left is positive. It's going to be positive k. K means how many times it has jumped to the left. Again, I can round this to 3 significant figures. For instance, 8.56 times 10 raised to the power positive 3, which is 3 significant figures. There you go. So these are some of the rules that how you convert a decimal to a scientific notation. And if you have a number, let's say 86400, I can convert this also into scientific notation, because I know the decimal is somewhere here, because I can always write 0.0 like that. So I need to convert this back, the 1, 2, 3, and 4. So as you know, it moves 4 units to the left, so I can write 8.64. I don't need to write 000 because 0, it's fine until here, it's okay, times 10 to the power of positive 4, because it has moved to the left 4 units. So these are the ways how you convert it to scientific notations. You can also use your calculator to get your answer directly into scientific notations. You just have to do some setting that we'll see in the questions. A circle has a diameter of 6.24 centimeter. Find the area of the circle, rounding your answer to A part 3 significant figures, B part 4 decimal places. Pretty straightforward. We know that the diameter is 6.24 centimeters. We know that the area formula for circle is pi d over 2 squared. Reason, we know that the area is pi r squared, and we know that r is diameter divided by 2, or half of the diameter. I just substituted r as d over 2 here. So my A would be pi. It would be 6.24 over 2 squared. If you just put in the calculator, remember always to use pi in the calculator. Do not use 3.14, something that is a built-in irrational number pi in all the calculators. Try to use that. So our answer for area comes at 30.5815195 and so on and so forth. Now I need to convert this into 3 significant figures, which means I need 3 significant figures. 1, 2, and 3. So I need to check the next number, whether it's greater than 5 or no. So 8 is certainly greater than 5. So my area would be 30.6 centimeters squared. This is 3 significant figures. To convert into 4 decimal places, approximate into 4 decimal places, my area would be, my 4 decimal places are 1, 2, 3, and 4, which means I have to look at this digit. So this is less than 5. So that means my previous digit will not change. That will be 30.5815 centimeters square, correct to 4 decimal places. So this was a simple approximation question. The second question says, the speed of cricket ball is recorded at 141.6 kilometers per hour, rounded to 1 decimal place. In what range of values does the actual speed lie? Now, I told you that, for example, if I write speed as 141.6 kilometers per hour, in this case, it's rounded to 1 decimal place, which means my smallest division is going to be 0.1 kilometer per hour. And we know my error will always be equals to half of the smallest division. So in this case, it's going to be half of 0.1, which is 0.05 kilometers per hour, which means that my speed is in fact 141.6 plus minus 0.05 kilometer per hour. So that's your range. So if I want to check the lower bound of speed, it's basically 141.6 minus 0.05. This is basically 141.55 kilometer per hour. Similarly, upper bound is 141.6 plus 0.05, which is 141.65 kilometer per hour. Which means I can write my speed range as 141.65 kilometer per hour to 141.55 kilometer per hour. The next question says, Tara measures the dimensions of a box as 15 centimeter by 12 centimeter by 8 centimeter, rounded to the nearest centimeter. A part says, use Tara's measurement to estimate the volume of the box. This is the same way as we did for perimeter or something like that. Now, the A part says, use Tara's measurement to estimate the volume of the box. To estimate the volume using the measurements, remember whatever you have measured, that's what the estimation is all about. So volume approximately would be equals to 15 centimeter by 12 centimeter by 8 centimeter. This will be equals to, which is the approximated, remember this is the approximated volume, so that's why I wrote A with it. So it will be 1440 centimeter cubed. So this is the approximated value. The B part says the actual dimensions of the box are 15.3 by 11.8 by 8.4. It says B part, find the actual volume of the box. So I will use the terminology VE. So the actual volume is 15.3 times 11.8 times 8.4. And the answer is 1516.536 centimeter cube. The second part says find the absolute and percentage error. So I know my absolute error is basically VA minus VE mod, which is basically the approximated, which is 1440 minus 1516.536 centimeter cubed, and my absolute error, although it's a negative, but we'll write the positive absolute value, which is 76.536 centimeter cubed. This is my absolute error. And what is my percentage error? Is basically the absolute error, which I found, over the actual value, the exact value times 100. So this will be 76.536. The actual value is 1516.536 times 100. And you would see my percentage error is 5.05%. So the next question is simply using your calculator to find the values of these things. In order to convert all the calculations into scientific notation form, you need to go to Shift menu and go all the way down to display. Right now, the display is set to normal. You need to convert it into scientific notations. Now this is asking you until what significant figures you need to approximate the numbers. So in this case, I'm selecting 3, that my answers will be converted to 3 significant figures. Now I go back, and now I will just put in my values and start and get my answers in scientific notation. The first question says that I have to multiply 3.57 times 10 power 6, multiply it by 2.38 times 10 power 3. If you see, I get my answer as 8.50. E means times 10 power 9, positive 9. This is rounded off to 3 significant figures, as you can see, 8.50. The second question says to divide, so I use the fraction thing, and I'll divide 4.61 times 10 power negative 7 by 3.45 times 10 power 8. And if I simply execute this, I get 1.34 times 10 power negative 15. The last thing that I need to do is find the power of 0.00008 power 4. If I execute, I get 4.10 times 10 power negative 17. So this is how you can convert into into scientific notations. And if I want to go back, I can just go Shift menu and go all the way down to my display and convert into normal.